All right. So we're going to talk about a couple of specific applications of the dot and cross product. We will do other things with them, but these are kind of the two primary places you'll see them applied in other places. The first one is work. So when we talked about work before, our force was we were always working with force that was in the direction of motion. So the work done by a force so we're going to say a constant force F acting along some vector PQ. So in in the direction from point P to point Q is the magnitude of the force times the distance that we move. So the magnitude of PQ. And when we did our pumping problems and our lifting problems, usually the force that we were talking about was either gravity or the force that the pump is applying to the liquid, that kind of thing. But it was always in the direction that we were moving it. If our force is not in the direction of motion, we're going to have something like this. Draw a little picture here. So here's our direction of motion, like so. And this is our vector PQ. And our force is acting at some angle to PQ. So there's F. Only the force that's in the direction of work or in the direction of motion does work on whatever the object is. Well, the force that's in the direction of motion, we can draw a nice little triangle here. The magnitude of this, the force in the direction of motion, is the magnitude of F times the cosine of theta, where theta is the angle between those two vectors. So our work done is, I'm going to say W is the magnitude of F times the cosine of theta times the magnitude of PQ, the distance that we move along that vector. Well, what is that quantity? Magnitude of F times the magnitude of PQ times the cosine of the angle between them. That's F dot PQ.
What is it FD? Force times distance.
Force times distance. The force in the direction of the distance times the distance. So that F cosine theta is the component of the force in the direction of motion. So we can use a dot product to find work if our force is not acting in the direction of motion. So this would be like you're dragging something along, but you're holding with a rope. And the rope makes an angle. It's not directly horizontal to the ground. And the portion of the force that's the vertical portion of the force is lifting the whatever the weight is if you're dragging it. So that reduces your coefficient of reduces your frictional force because you have a smaller normal force on you. We can also recognize. This is a little this is the notation that we'll use most of the time, but you'll see in the book occasionally, and you'll see in other places, that a slightly different notation for this. So we recognize that the magnitude of f times the cosine of theta is the magnitude of the projection of f onto PQ. So projection onto PQ of f. This is how we came up with our method of finding vector projections, vector components. We saw that this was the magnitude of our vector projection. So we can also write that the work is this magnitude of this projection forgot my vector here, times PQ, times the magnitude of PQ. So this is just another notation that you will occasionally see for work when the force is not in the direction of motion. For the most part, we'll always use this. You might see this in textbooks sometimes. So you might see that somewhere. And what we're going to do second semester is use this idea, this F dot PQ idea, to talk about how we find work done by a force that's not acting on something that's moving in a straight path. So we can have some kind of curved path in three-dimensional space and some force acting on some object, and we can find the work done for the object moving along. Yeah, exactly, Sam. The hard part is going to be describing that three-dimensional path in space. But we come up with a method for finding that work done, and we'll develop what we call a line integral. All right, so quick example. We have a force that's given by F equals 3 I hat plus 4 j hat plus 5 k hat. And it moves a particle from point 210 to point 462. We want to find the work done. Easy problem, easy method for solving this. When our motion is in a straight line, these problems are pretty easy. PQ we find by terminal minus initial, so that's going to be the vector 4 minus 2 is 2, 6 minus 1 is 5, 2 minus 0 is 2, and F dot PQ is just going to be 3 times 2 is 6, 5 times 4 is 20, 2 times 5 is 10, so we get 36. Our units of work in international units are Newton meters or joules. And we say Newton meters because our force is in newtons, our distance is in meters, so Newton times a meter. Well, the dot product incorporates that. Right. In imperial units, we can do foot-pounds or inch-pounds. So those are our units of work in imperial units. Sometimes you'll have Newton centimeters. for smaller increments of work.
Why can't you just do that earlier? With the smaller number of joules.
Yeah. Yeah.
So when it says Newton meters, is that like Newton dot meters?
Newton times meters.
Times, okay.
Because we have a magnitude. Let me go back one slide. Our work is the magnitude
It works.
of F times PQ, so that's newtons times meters. So the magnitude of our force is in newtons, the magnitude of our distance is in meters. All right, questions on work done by a constant force not in the direction of motion. Not extremely interesting application, but it is an application. Next semester we'll work no pun intended, a little more with this idea where our path is not a straight path. All right, torque. Our torque is one of our applications of the cross product. Our definition of torque is the moment and we're going to talk about a vector moment, m of a force F about a point. And remember that a moment is a quantity weighted by its distance from some axis. This is a parentheses. So we're interested in this the distance the distance of this force from an axis, and the bigger the distance, the bigger the moment. The smaller the distance, the smaller the moment. All right, so let me draw a picture here. If we have some vector PQ, like so, and we have a force that's acting, so say this is a lever or a bar or a wrench or something, some physical object, and we have a force that's acting on that. So we're pushing on the wrench, we're pushing on the bar, we're lifting on the lever. And this is F. Our torque is going to be orthogonal to PQ and to F. So this dotted line is parallel to F. So we're orthogonal to both of those. And that is our torque. So, and this arrow shows the direction that thing is going to tend to rotate if we push on it with that force. So we're going to say if our force is acting at Q, our torque is given by PQ cross F. And the torque tells us the tendency of PQ to rotate about point P. And we're going to say to rotate counterclockwise. Counterclockwise is going to be our positive torque. And our axis, I'm going to say our axis is along vector M. So our torque is a tendency of that lever, that rod, whatever, to rotate in the counterclockwise direction. And if it's rotating counterclockwise, we say our torque is going upwards. And we think the torque is in the direction that a normal screw would turn if you turned it in that direction. So if you rotate a screw counterclockwise, it's going to loosen. It's going to come out. Righty tighty, lefty loosey. And we find the direction of the torque, PQ cross F, using the right-hand rule. So if your force and if you put your fingers in the direction of the force and the PQ, your thumb points in the direction of the torque. I tend to think of the cross product as an action. So I think of the force, or PQ, the force being in the direction of my palm, and my fingers being PQ, and you cross PQ onto F, and the cross product is in the direction of your thumb. So I think of the cross product as an action. You're crossing a vector onto the other. That helps me visualize it.
It's like those like automatic drill things.
Right. The magnitude of the torque the magnitude M, not of, is PQ times F times the sine of theta. So we said that's when we do a cross product, that's our magnitude of the cross product. This quantity was, I'm going to say, where theta is the angle between PQ and F.
So where would that be on this diagram, at the angle at the point that I need?
Yes. Or we could move them tail to tail, and it would be, yeah, same angle, yeah. And I'm going to change pages, and I'm going to draw another diagram. This quantity F sine theta is the component of F that is perpendicular to PQ. So when we did the dot product, we get the component of our force that's in the direction of our vector. When we do the cross product, we get the component of, this gives us the component of the force perpendicular. So let me draw another picture. If this is PQ, and this is F, and this is theta, this component is the magnitude of F sine theta. This is a 90-degree angle.
So is this in one plane, that diagram?
What's that?
That diagram's in one plane.
In one plane. So the torque here would be coming out of the page. M would be coming out of the page. So this quantity, F sine theta, is the component of F perpendicular to PQ. Only the component of the force that's perpendicular to our the vector PQ produces torque. And we call that F, magnitude of F sine theta, is called the moment arm. So if you're pushing on a wrench, and only the component of the force that's in the direction, or it's perpendicular to the wrench, produces torque, how do you want to push the wrench to produce the most torque? You want to push perpendicular to the wrench. You don't want to push along the wrench, you want to push perpendicular. And the other way you can produce more torque is make your wrench longer. All right. Questions about torque? Okay, let's do a quick torque example. So I remember learning physics when I was in physics in high school, learning about torque, and always calculating torque by doing F sine theta. And then when we learned about the cross product, I was like, why did we ever do F sine theta? Why didn't we always do the cross product? All right, so for our example, we push a push a 3-foot horizontal bar with an upward force of 20 pounds. At a 70-degree angle to the bar. We want to find the magnitude and the direction. So remember that torque is a vector. So let me draw a little picture here. So here's our 3-foot bar. And here we are pushing with a force of 20 pounds. And this angle is 70 degrees. So there's our diagram. So maybe the end of the bar is in an awkward position, and we can't get quite the angle to push at a 90-degree angle. So we're limited to push at a 20-degree angle, or sorry, a 70-degree angle. There's a shelf in the way or something. Who knows? 3-foot bar is a pretty long bar, though. All right, the magnitude of our torque is just going to be the magnitude of PQ cross F. And that, in this situation, is just going to be the magnitude of PQ times the magnitude of F times the angle between them. And I get that is about 56.4 foot-pounds. What's the direction of the torque? If we cross PQ, there's F, there's PQ, we cross PQ onto F, the torque is out of the page. And if we thought of this as turning a bolt, if we push the wrench this way, the bolt is going to loosen, the bolt is going to come out.
So if you were to do this on a test, what would you do for this? Just
Say out of the page. Yeah.
perpendicular to the paper?
Yeah, perpendicular to the paper, out of the page. If we were pushing the other direction, the torque would go into the page.
I'm confused. That's the thing.
Yeah, so I just think about like that.
So which,
It's like this.
Whichever way it's turning, so turning clockwise.
right, that, yeah, that's
Or, I mean,
fine.
counterclockwise,
Right, or
clockwise.
clockwise.
Thumb's going out. That
Um,
makes sense. It's going in.
So that's fine if you visualize it as turning. I think of PQ, my fingers being in the direction of PQ, and F coming out of my palm. So if I'm crossing, so here's PQ and here's F. So when I cross PQ onto F, my thumb's coming out of the page. But if F were going the other way, I'd have to cross PQ onto it that way, and my thumb would be going out of the page.
So we can always draw it.
I like
So
this.
we can always draw these cross product things as a flat diagram just by looking at the vectors part. And the cross product part will always be perpendicular to the page if you draw it
Right.
with those vectors flat.
Right, but if you're given the components, the vectors in component form, and you have 2 3-dimensional vectors, it's harder to draw them flat and visualize it that way. So then you have to visualize PQ cross F. All right, questions? So if you ever are asked to calculate the scalar triple product, there's a nice way to do that.
Other than visualizing parallelopipeds.
So we said the scalar triple product or the box product was the volume of a parallelepiped with the 3 vectors as sides. So that's A dot B cross C, which is equal to A cross B dot C. And we said that that was the volume of this squashed box with A, B, and C as adjacent sides. We can calculate that by doing this determinant. Whoops, A1, A2, A3, B1, B2, B3, C1, C2, C3. So you calculate that 3 by 3 determinant, and that will give you the scalar triple product. So it's just a nice way to calculate it. All right. Questions about our application ideas?
I think we might have been tossed out. Wow.
All right, there you go.